A very good evening to all of you. So today we will be understanding the second stage of the operational amplifier, and that is the intermediate stage. Now, as you know that the operational amplifier is made up of the four important stages. The first stage is about the dual input balanced output differential amplifier. Then second stage is about the dual input unbalanced output differential amplifier. Third one is the level shifting stage, and the fourth one is the output stage. Normally in the output stage, you will find the complementary symmetry push-pull amplifier, which is going to amplify the or which will transfer the maximum power to the load. The load can be anything. It can be a resistive load or it can be a speaker. Now coming to the input stage, this one we have studied earlier, and this input stage will be requiring two input signal. So one input will be applied to one transistor and the second input will be applied to a second transistor. It means that this input stage is a combination of the two transistor, and these two transistor will be a matched one. So how you are going to draw it? So this is the RC. Okay, I'm drawing. Normally we use the common emitter configuration. Then after that, this is the input signal which you are going to apply. This input will be having a source resistance, and after that, this is the input signal. Then for having the match a transistor, you need to satisfy certain condition, and those conditions are that the VBE for both the transistor should be equal, then the beta value is also equal, and at the same time the beta should be very high. Okay, so this is the biasing voltage which I have drawn here. So now this one is shorted, the emitters are shorted, these two are very much symmetrical. So this is RS2, then you are having VS, sorry, V2, this one is V1, and here you have drawn RE, and this is minus VEE. I told earlier that this operational amplifier IC will be requiring two power supply voltages, and these power supply voltages will be ensuring the what you can say, the reverse biasing of the reverse biasing of the collector base junction and collector emitter junction, and the forward biasing of the emitter base junction. So these are the biasing voltage which will be requiring, and these are supplied through RC and through RE. So this was about the dual input balanced output. Now why we are saying it is balanced? Because we are taking the output from both the collector terminal. You can see that this V1 will be multiplied by the gain of this transistor, and this will be multiplied, this signal will be multiplied by the gain of the transistor. So the output voltages are going to appear here. Now this one is V01 and this one is V02. So depending upon your we can say multimeter, you can measure the output voltage. Suppose if you are taking, if you are keeping the red terminal here, so that will be considered as a positive. So in that case, it will be V02 minus V01. So this is not the point of discussion. The point of discussion today is about the unbalanced, that is the dual input unbalanced output, and that is the intermediate stage. Normally, this input stage provides the high value of the gain to this operational amplifier, and at the same time, this input stage is providing the high input resistance. As told earlier, that for the good amplifier, you will be requiring four important things. That is, you require high voltage gain. High voltage gain will be required. Then you require high current gain, high current gain, you require high current gain, then you require high value of input resistance and low value of output resistance. These four things you need to consider while selecting the amplifier, while selecting the common emitter configuration for the amplifier. Fine. So now coming to the unbalanced output. Unbalanced output means what? Unbalanced output, it means that you won't be requiring, just a minute, you won't be requiring um, you won't be taking the output from one of the collector terminals. So I think this one will be we can rub it out. Now you can see that that you have taken one terminal is at the collector and the second one will be at the ground. It means that you are measuring the voltage with respect to ground. So what you will do, you will just take this here, and you will have to measure the output voltage with respect to ground. So this is called the unbalanced output. Again, this intermediate stage is going to provide the high voltage gain for the what you can say, this operational amplifier. So this one is A1 and this one is A2. So A1 will be multiplied by A2. Obviously this is a direct coupling. You are not having any capacitor in this operational amplifier IC. So this is a linear IC, we can say, because this IC will be having only the linear resistors, or you can say resistors. That's why it is called linear IC. So now we will try to analyze the things. So you can perform the DC analysis and the AC analysis. I think we have already performed the DC analysis. So for the DC analysis, what you will be requiring, you need to remove the AC sources, or you will have to replace the AC sources by its internal resistance. Just a minute. So I'll be replacing this source by its internal resistance. So when you are replacing, so that time this will be right. That time this will be only RS1 and this one will be grounded. So we have replaced the thing, and this one will be grounded. So now you can see here you will be having only the DC voltages in the picture, the collector resistance, then the emitter resistance, then the RS1, RS2. So as you know that these two are the match transistor. So the match transistor, it means that the base emitter voltage are equal. So I will write only VBE. Similarly here I will write only VBE. Fine. So now you can see that all the voltages are common, biasing voltages are common to both the transistor. Even you can see that the biasing resistors are also common. So it means that the current will be, okay, I'll assume the current, that this is the base current. As you can see that this is the NPN transistor. So you will be having N here, then P here, then N here. So the direction of the current is always from P to N. Fine. So now this one is IE, and this is also the IE. So we can see here this one will come, this will IE plus IE. So that one will become twice IE. I think I have already explained this while doing the analysis of a dual input balanced output differential amplifier. So now you just have to you can say apply the KVL. Either you can apply KVL at this a transistor, or you can apply KVL at this a transistor. Okay, so we'll be writing the things. So now when the current is moving in this, or you can say inside, so this one will be plus and this one will be negative. So this one will be plus, I'll just mark it out. Okay. So coming here, so RS into RS1 into IB, RS1 into IB. Normally this RS1 will be in ohms, so you don't have to worry about it. And as beta value is very high, what we can write, as beta value is very high, so we can say that IC is very high, or you can say IB value is very low, or it is the at the minimum, that is lowest. So in that case you can see this IC is nearly equals to IE, because if you are doing the DC analysis, it means that you will be requiring the operating point. Fine. And normally to locate the operating point and to make the operating point stable, we are doing this DC analysis. We need to find out what are the operating conditions of the transistor. Fine. So this, because beta is selected as a very high value, so that's why you can neglect the value of IB. So in that case, your IC current, you can see here the IC current is flowing. This is the IC current. Fine. This is the IC current which is flowing. Same. This is the IC current which is flowing. So IC is nearly equals to IE. Okay. So leaving aside all these things, so now this one is a plus VBE. After that, there is a wire, we can say. So now you can see here IE plus IE, these two currents are entering into the node. Fine. And then this current has left the node. So now it is flowing through the RE. So when it is entering into RE, we will have to mark that as plus, and this one is negative. So you can see that the current is moving from plus to negative. So that will be counted as the voltage drop, and normally in my sign convention I take it as positive. So after that we will be having the negative power supply. So this is the thing. So now you just have to, okay, can I write just a minute. I will have to write, I will have to find the value of IE. So in that case this one will be here. So VEE, then this one is minus VEBE upon twice RE plus RS1. Okay, just a minute. I think I have written 2 3 steps in one step, so that will create a problem. So instead of doing all this thing, what I can do that what I can do, this IB will be equals to what IC upon beta. So we have assumed that this IC is nearly equals to um, IE. So this one is IB upon beta. So now I'm writing here. So you can see here RS1 into, now you will have to write IB as IE upon beta, then plus VBE, then after that plus twice into IE into RE, and minus VEE will be equals to 0. I think this is okay to me. So now you can see here, you will have to find the value of IE. No, so first you take these two terms separate, or will write one more step to avoid any type of confusion which you might be having. So this is twice into IERE. This is VEE minus VBE. Now coming here. Okay, so I think I'll keep this as common. Okay, this one is plus only. Don't make it IE1. Huh? So IE RS1 upon beta plus twice into RE will be equals to VEE minus VBE. This is already explained in the input stage. So IE will be equals to VEE minus VBE upon this is twice RE. Let me write here twice RE plus RS1 upon beta. So you can see this is the operating current equation, IE, because you can substitute this IE, or you can replace the IE by IC. What you can see that this base emitter voltage is a temperature dependent variable. As you know that when the temperature increases by 1 degree Celsius, the temperature increases by 1 degree Celsius, then your VBE will decrease by 2 millivolt, 2.5 millivolt per degree Celsius. This is the relation which you already know. So I think this is temperature dependent. We cannot take a risk with this VBE. and this is the constant voltage because we are supplying externally, so this is the constant. This one is a temperature dependent. Just now told you that if you increase the temperature by 1 degree Celsius, so that will reduce the, what you can say, VBE. So when it is reduced, it means that the IC or IE will increase. Now, similarly, coming down to the denominator, you can see this is beta, and this beta is also temperature dependent. So, I think this will shift the operating point somewhere near to the saturation or to the cutoff. So, this is highly injurious. This is the constant current, but I think that this is not looking like a constant current because these two parameters are there which can shift your operating point. This is about the IC. So we have just calculated the first coordinate of the operating point. So now the second coordinate which you will have to find is, that is what? I'll rub it out. The second coordinate is, yes, the second coordinate is VCE. So how you are going to calculate the VCE? VCE means what? VC minus VE, that is collected to emitter voltage. Normally this load line is present in the output characteristics of the common emitter configuration, and that's why we will have to take only the coordinates of IC and the VCE. So I think how to find this one is collector voltage. Just a minute. I think I'll have to take the new color. That will right. That will ease out our process. This is VC and this one is VE. So how to find VC? So I think we will take this much section out. Even in the classroom, I think I did this. So I think this one is RC. Then you are having the what you can say, VC. So normally what is going to happen? I think I'll draw in this fashion. So that will be a lookalike condition. Okay, so this one is VC. See, okay, so this one, the current IC is flowing. So you will have to apply KVL up to this point only. So normally VC will be equal to what? VCC minus IC into RC. You can see here plus point is here and minus point is here. So minus point is coming down to the VC. Fine. So now VE, how to calculate VE? Again, you will have to, this is the, okay, this is the first equation which I have to write. And the second one, to calculate the emitter voltage, I think emitter voltage is not the emitter is not connected to the ground. This entire arrangement is here. Again, this entire arrangement. So you are having two options. Either you can traverse the path like this or you can traverse the path like this. So I think this is much more feasible for us. So I'll be drawing. Just have a look at my drawing. RS1 I have drawn. First it is ground. Then this is the transistor. This one is first transistor which we have taken. You can take this Q2 also, not an issue, because we are not much concerned about the output signal, that is the AC input signal. This is VBE and this one is VE. Fine. So what I can write, okay, so if I apply a KVL up to this point only, so you can see here you will have to apply KVL only up to this point. You don't have to go for the entire loop because our interest is only the voltage at the emitter terminal. So in that case, IB into RS1, then plus VBE, then this is plus VE will be equal to 0. You can see this is plus and plus. I think this point is plus and VE is measured with respect to some point. No, that's why this current will encounter the plus only. So now you can see that the beta value is very high. When beta value is very high, so the base current is very small. So in that case, you can neglect this term just for the simplicity. Even if you want to incorporate that thing into your equation, that is very much fine to us and fine to me also. So now VE will be equals to minus VBE. So this is the second equation. Okay, so I'll rub it out this. Okay, okay, just a minute. So VCC, so I think VCE will be equal to VC minus VE. VC, just from this equation you can write, uh, I think this one will be VCC minus IC into RC, and this one is minus VBE. Okay, so we have got, again, you can see this equation is temperature dependent because the VBE is appearing in this equation. So I think that somewhere these two coordinates are temperature dependent. So we cannot comment on the stability of the dual input unbalanced output differential amplifier. Same thing was there. You can just have a look. I think these two are the equation. You can see from the what you can say, this thing from the figure only you can see this is the dual input and balanced output differential amplifier. So we have got these two equations. These two are temperature dependent, and similarly if you just calculate the voltage gain. Now how you are going to calculate the voltage gain? So for calculating the voltage gain you will have to perform the AC analysis, and that time V out will be equals to what? V out will be equals to, what is the value? V out will be equals to what? Can you please comment on it? This is IC2 into RC, or IC2 into RC, and then so when you're performing the AC analysis, that time the DC sources are grounded, or you can say removed, or you can say short circuited. So in that case this one will be minus IC2 into RC. So IA2, now similarly like the thing which we have performed in the dual input balanced output differential amplifier, same thing you will have to do, same thing. The entire thing will remain same, but only this output will change because you are measuring the output voltage between one of the collector terminal and the ground. You are not measuring between the two collector terminal. This is the unbalanced output. So after doing all the calculations, so you will arrive at this equation, that is RC upon twice RU. So now you can just go through this equation. This equation is very you can say more structured. We can say that is AD will be equal to RC upon twice into RE. I will have to understand what is the value of RE. RE means what? This is VT upon ICQ, that is the DC operating point. So you can see here RE depends RE depends upon Vt, and Vt is what? KT upon Q, that is K is the Boltzmann constant, Q is a constant, that is a charge on a charge particle, and T is the absolute temperature. We cannot guarantee on this absolute temperature, that is going to vary, and if it is going to vary, this is going to vary the Re. So when your Re is varying, it means that it will have a direct impact on the voltage gain. So normally this voltage gain depends upon the Re. So I think if you keep your differential amplifier at some other temperature, so your voltage gain will vary. So voltage gain depends upon the temperature, and this should not be I think this is not acceptable for our differential amplifier, or you can say for our operational amplifier. So we need to make our differential amplifier independent of this variation. You can see Re will vary because of the temperature. So I think in the next class we'll be studying about the swamping resistor, which will eliminate the temperature variation, or which will eliminate the Re parameter variation. This is all for today's class. We will meet for the next concept. Thanks a lot.